Okay, my name is Sara Seager. I'm a professor at MIT. I'm an astrophysicist. I work on planets orbiting stars other than the sun. We call them exoplanets.
Other than the sun?
Stars, yeah.
So the sun is a star, and
Yeah,
there are more stars like the sun.
Every star in the sky is a sun. And there are literally billions of suns or stars in our galaxy.
So, like the sun, we see the sun as that's the center of the universe.
Oh yeah, well the sun is more or less the center of our universe, but our sun is just one of billions of stars, hundreds of billions of stars, orbiting, all bound together in a galaxy we call the Milky Way.
Wow.
Yeah, so many stars. And now we actually think that every star has a planetary system. So if there's hundreds of billions of stars, there could be trillions of planets in our galaxy alone. And actually, there are hundreds of billions of galaxies out there. So that's one followed by lots of zeros.
Wow, it's too much. It's already too much. One question,
Yeah.
and it's too much. Wow. So how do you know? Because it's unimaginable.
Well, it took decades, if not centuries or thousands of years, for us to figure out what's out there. But actually, now astronomers have found planets, thousands of them. Everywhere we look, every star that our technology can find a planet around, we do find a planet, almost every star. And so we just are piecing it all together about the range of planets and what's out there. We also see star-forming disks. We see that when stars are...
Disks?
Oh, disks.
Disks.
Yeah. We also see when stars are born, they're born with a gas... They're born... We also see when stars are born, they have a disk around them that's kind of full of junk, leftover material. And we see that around almost all stars. And out of that junk, that dust and gas that's left over, planets are going to form.
Like the Earth formed.
Like our planetary system formed. Yes, that's right.
So, but then again, how do you know? How do you know?
How do I know myself?
You have to. Do you have to
Right.
believe it? Or
Actually, you
have-
do. That's kind of one of those complicated things in science because we can't repeat every experiment ever done. Like, for example, my building at work, you'll see it. You're going to love my office. And if it's a clear day, even if we're not filming up there, I'm going to take you up to the roof because we can see the entire city skyline of Boston. We can see over to the ocean if we're lucky. If it's a clear day and we climb up this little crow's nest ladder that leads to a little crow's nest, we can see over to the White Mountains in New Hampshire. Now, I'm guessing you wouldn't want to jump off that building because you believe in the laws of gravity. So some things are accessible to us. We believe in gravity and we believe in some laws of physics. Well, we believe in all the laws of physics, but some of them are accessible to us. So it's kind of a complicated thing to get into right away, but in science, we believe on these building blocks, starting with things that we experience, and some things get more complicated and more abstract. Now, when it comes to exoplanets, in some cases, the measurement of detection of that planet is incontrovertible. We really can't ascribe it to anything else but a planet. In other cases, we see like an indirect measurement of a planet. And in that case, sometimes it's a bit of a leap of faith to believe it's a planet. And in some even more extreme cases, a planet detection will later be retracted because it looked like a planet was there, but it turned out to be something else. It's like noise. Like I'll give you an analogy that will make sense to you. If you take a picture and it's very grainy and blurry, you think you see something like a UFO, and you're not sure. It kind of looks like it's something you can recognize. You're not 100% sure. Later, you go back and take better images, and you see what you thought was there was just a noise. It was just nothing, an artifact. So we sometimes see that as well.
So, what exactly is your position into this exploring?
I have many different positions in this field. The one I started out in is studying planet atmospheres. Like on our own Earth, we have air that we breathe. All these other planets also have their version of air. It might be hydrogen or helium, or it might be carbon dioxide or something else, but it's to study these atmospheres of planets far away and to try to understand what those atmospheres are made of. That's my main... that's one of the main things that I started out doing.
And are you the only one?
There's lots of people working on this now. When I started, there were very few, almost nobody was working on this. But now it's amazing, actually. If I could Yes, it's just remarkable now that the things that the field was so new when I started that people were finding planets. Other people accused the people finding planets of stamp collecting. You're just collecting these things. What are you going to do with them? It's hard enough to find them. And many of the findings people didn't believe. So they're wondering, why was I wanting to study their atmospheres, which is even harder to do. So it's amazing now that today, it's 20 years later, not only do we have dozens and dozens of planet atmospheres measured, but it's so standard now. Like, you can come to MIT and go to a talk next Tuesday. A visiting professor will be talking about exoplanet atmospheres and how complex they are. It's now bread and butter mainstream astronomy. So there's lots of people working on it right now.
So what kind of proof do you have to deliver? Like an atmosphere, how can you tell people, well, this is real, this is proof of a planet? Or do you have to show them a picture?
Yeah, it's a really great question. I wasn't expecting such a hard question. But actually, again, we build on many decades of work. So for a long time, astronomers have used spectroscopy. We break up the white light of the sun or a star into different colors, and we look for lines that are missing, little pieces of, let's say, the rainbow, the spectrum, that are gone. And from that, we infer the presence of atoms and molecules. So if you want to know the truth, people before us did all the hard work. When they did all the hard work, even looking at the sun and stars, we can see many different atoms in the photosphere of the sun and stars. And, it took people a long time to believe that stars were made mostly of hydrogen and helium. So the tools we use and the applied physics we're using and the atomic and molecular physics, people worked hard to understand that and fought with each other about what was believable and what was not. So we're taking this decades-old technique and applying it to planets. And so we have two problems. One is to get good enough data so we can see a robust signal. Again, like back to the image, you can have a very blurry image in low light, and you could think you're seeing something, and you wouldn't be able to prove to someone else that you're really seeing the scene you think you're seeing. So we have to have good enough data so everybody can look at the data, every astronomer, and they'll say, yes, I do see a spectral feature, I do see a signal above the noise.
And that's data is like, it's not a picture.
It's not a picture, no.
So what is it?
I could, well, I'm going to think of how to explain this to you. I do have
because then you have to prove by interpretation of figures.
Yes, we do. Like, I wish I could show this to you. Maybe tomorrow I can show you a picture. I have a nice printout at my office, but I'm just going to walk you through it now. Yeah. But what we do is we imagine for a moment you see a rainbow. If you could look at that rainbow very closely, you would see that some parts of the colors are missing. You would see literally, out of that rainbow color, the red, orange, yellow, green, blue, you would actually see little pieces that look black lines, as if someone took a marker and just drew a black line. And we do that in astronomy. We break up the white light of the sun or stars, and we see some lines missing. But those lines aren't just sharp. They may have a gradient at the edges, so be a bit fuzzy at the edges and very dark in the center. And believe it or not, in the old days, people would take photographic plates, and they would record these, they'd have a prism that broke up the light into colors, and they would literally see these dark lines. And they'd put it on a table and shine a light through it, and then they would measure how much light gets through where these dark lines are. And from that, they would make a curve. So now, no light, let me think of this. Okay, so they'd say no light's getting through, then all of a sudden, a lot of light gets through. But it would be some kind of curve that is some width. And then they'd have another little blip and then another one. And that's how we make a measurement of a spectrum. Not with photographic plates anymore, it's all digital. And from that, yes, we have to do interpretation. But we understand how atoms and molecules absorb radiation, both from calculations of quantum mechanics and also from laboratory measurements. And so, yes, it might seem like a leap of faith, but we are building on knowledge and tools that have been used for decades for astronomy and for Earth atmosphere observing.
So now you are doing the hard work for future scientists.
We're doing, yes, in some ways, yes, we are doing the hard work for future scientists, because the signals we're studying now are so weak and so faint, and the techniques we have to use are brand new compared to how we study stars in our own Earth's atmosphere.
So why are you so attracted to finding an exoplanet?
I'm going to have to think about that for a minute. Let's see. Like, by the way, that's just a tough question to ask because each of you could ask yourself the same thing. Why are you doing what you're doing? No, at some level, we just don't know. I mean, we do it because we just love doing it and it seems exciting and fun and it's amazing. But I have to say for myself, even ever since I was a child, I always wondered what is out there. When I saw the sky for the first time, the dark sky, really, really dark, tons of stars. It's like so many stars, I couldn't believe it. I'd never even known that that was out there. Ever since I saw those stars, part of me has always wondered what else is there. But there's another attraction too that's a little more, there's that one thing, that sense of wonder, but that's not what happens on a daily basis because we're just, getting through the day and getting our tedious work done. But there's this other really beautiful thing in science, and that is that you can explain the world around you with equations. And just the fact that we can write down basically starting with some very basic laws of physics and then some more complicated ones like with quantum mechanics and gravity and pressure, and we can work through all these basic things, these building blocks of physics, and describe an atmosphere far away and get data with the Hubble Space Telescope and actually interpret all that and make sense from it using basic physics is very satisfying.
I can imagine that. Is there also a chance that you will discover something?
I mean, we have discovered a lot of things. They're a little more academic in a way.
But what happens to you when you are researching and you were studying all these data, mm-hmm. and suddenly you see something? Hey,
it's not quite that, that abrupt that you see something. So I can try to think about. Okay, no, I can't explain that. Yeah, let's see. Yes, the times when we, like my team or I, get data and see something that's just so shockingly unexpected, it's extremely exciting. It doesn't happen very often. And sometimes it happens and it turns out to be nothing when you go back and take more observations. But, that moment of discovery is just amazing. It doesn't happen often enough to be the main reason why I'm a scientist. But it's definitely exciting. I have a different type of excitement, though, and the reason why I do it is, like, I can conceive of an idea of something that just seems truly unheard of and amazing. And then it can take a year or two or more sometimes to just work through the possibility. And when you find out that something, this crazy thing you thought of turns out to be right, that's a discovery. I can maybe work on trying to articulate this, but, there is that sense of discovery of getting data and seeing a signal and going, wow, I just can't believe we found this. I can't believe a planet like this one I think I found exists. That's definitely an aha moment. But there's another more complicated aha moment where we conceive of something and work through a project and you find something just totally amazing that you hadn't thought of finding before. And that is just so amazing. And actually, one of these, I'll just tell you a little bit about it because it's my favorite project right now. And you'll meet one of the team members tomorrow at work. We'll talk. And Remy had specifically asked us to talk about this. But it was actually, I was working on a project about biosignature gases that life might produce. And at that time, Charles and I, we actually just were celebrating our first year of marriage. But at that time, we were just kind of getting to know each other. And he had asked me a question. And Charles had asked me, well, out of all those molecules in our atmosphere, in Earth's atmosphere, how many of those does life produce? And it was an amazing question because I looked it up. I didn't know. And I went through tables of what's in Earth's atmosphere. And I found that every gas in our atmosphere to the part per trillion level by volume. So if you would capture part per trillion. So if you would to capture like a canister of air and measure how much gas is in there. And like, for every cubic centimeter, 1 part in a trillion is a certain type of gas. So all gases in our atmosphere just means many of them. There's about 3 dozen of them up to that level of abundance. They're all produced by life. Now, most of them have a dominant production from some other source, like geophysics, like volcanoes or photochemistry in the atmosphere. But they're also all produced by life. And this is amazing. And this is the type of thing that's like, is that just some weird coincidence or does it have meaning? And so that actually worked with the project I was already working on about the range of gases that life on Earth produces. It set off a kind of chain of events because I had a theory that I thought, partly based on this question about what's in our atmosphere, that life produces all gases. I thought perhaps life produces every single gas we could ever imagine. And so I started on a long project. I had to convince two of my biochemistry colleagues. Well, I had to convince one of my main colleagues. He works in biochemistry to do the project. And he thought it was silly, actually. He thought it was the most silliest thing he'd ever heard. He refused to work on it.
And then you think you're right.
Yeah, right. Well, then I managed to get another person interested, and I did a kind of scientific matchmaking between these two people, and all three of us started to work on the project. And ultimately, we collected a list of all molecules that are in gas form at temperatures, we call them standard temperature and pressure. That's our like room temperature, room pressure, surface pressure on Earth. And we found that it's not true, actually. So in this case, despite this excitement that I might have come across this concept that life produces all gases, it turned out to be completely wrong, actually. And it's not so. It's only true that life produces about a quarter of those gases, a quarter of everything. But we found something even more interesting, actually, on this journey, that in this set of molecules or molecular fragments that exist in general, that there's certain pattern amongst the fragments of molecules that life doesn't produce. So life seems to prefer producing some types of molecules, and other types of molecular fragments life never produces. And so right now we're pursuing that avenue of research to see what it entails. And we think it may actually be very helpful in the end for toxicology and perhaps even pharmacology. So that actually it's so exciting because we started out with one thing. It's like we're trekking to the South Pole. We have a goal, we're going to get there, we have a destination, we want to go to the South Pole, but instead we discover something else, that there's this mountain in Antarctica, it's really worth exploring, and we hike up that mountain, and we went the wrong way, then we have to go a different way, and finally we get somewhere that was just so breathtakingly amazing, we never conceived of it. And we're in the process of doing that now, and we're not at the point where we can say that we found something amazing, but I really feel strongly that this is going to be awesome.
But do you have the impression that you are in some kind of wilderness?
Let's see. Okay, that's a good one. Sometimes, yes. Sometimes I feel like I'm in a wilderness.
And how are you equipped?
Well, in this particular wilderness, the funny thing is we have to learn our skills as we go. It's like we're only outfitted with the most rudimentary gear, and we have to develop our tools and find out what we need as we go, actually. It sort of reminds me, too, a bit of exploring. I used to spend a lot more time in the outdoors than I do now when I was like younger. And you'd go on a trip and not know what you were doing. We'd go on a trip and maybe you'd make a mistake and something would go wrong. Maybe you're just wet all night because your tent was leaking or you had some problem. And the next time, you can go home and think through what you did wrong and go back out there and do a better job. Stay out for longer, be more comfortable, be more skilled at navigating. And so we have a chance to go back and learn things. I learned Python. It's a now language that everybody knows how to use. So it wouldn't Python. Mm-hmm. Okay, so you guys don't know how to use it. It's a computer language. Yeah, computer language. Okay, because if you said, I just learned Python at MIT, it'd be like, really? You're like a child. Okay, so what happened was, it's like, I'm liking that skill. I needed a new skill because what we're dealing with is, it's a big data problem, an informatics problem. And we have to, we still, just like the explorer in the outdoors, we can go back and outfit ourselves in a better way. And that actually involved just learning a new skill. So I did learn how to program Python. I did like an online class. You can, with Python and programming, it's like learning a language. Like you can you can go, let's say, to somewhere foreign to us, like let's say Asia. You could pick up a few words, enough to get around. Or you could decide you're going to learn that language very thoroughly and do it right from the start so that you have what you need to get through whatever situation you'll encounter.
So for you, a tool was to learn Python language?
Python computer programming language.
To better know how to interpret data.
Well, it was more because we now have 14,000 molecules. What are we going to do with them, or the fragments of molecules? And we have to now compare those to lists of toxicity, molecules that are toxic. We have to be able to go to websites and get information by what we call scraping them. And we have to go and retrieve a lot of data. We have to, be able to mass compare things with each other in a way that this particular language makes it very easy to do.
Is there also a danger?
Oh, is there a danger? Let me think.
Because you mentioned toxic.
Oh, right. In this case, what I mean is in this case, what we're trying to do is see whether the fragments of molecules are building blocks in any way for anything related to life on Earth.
Yeah.
And
But if it's toxic,
well, they're not toxic chemicals. We're just doing things like in our computer.
no,
Yeah.
but I mean, when something is toxic, does it mean it cannot produce life?
Well,
Or
yeah, let me explain a little better. But in this particular application, it's not related to exoplanets. What we're thinking is that this, our ginormous database now that has molecular fragments and molecules that we know if life, we don't know, but we've tabulated from the literature that whether life produces it or not. If there's a bunch of molecules or fragments of molecules that life is not producing, and those same molecular fragments or molecules show up in toxic chemicals, it gives us a clue about new chemicals that may be toxic.
yeah,
I hope that was helpful. We're just trying to see what this, what we think that the information we've gathered on molecules and whether or not life on Earth produces them, whether it has some other application somewhere in environmental science or in drug discovery here on Earth.
So you are a physicist, but you are also an astronomer.
That's right.
And what is your main quest?
My main quest is to find another planet like Earth and to study planets to see if any of them have signs of life.
That's a big question in science fiction.
It's a big question, and it's a great job. It's a great quest because science fiction has laid out so many possibilities for us already. And we like to say science fiction is becoming science fact, at least in terms of our research.
Are you sure that there's life out there?
I'm sure there's life out there somewhere. There are hundreds of billions of stars in our Milky Way galaxy, and we think there are hundreds of billions of planets out there. So
why do you think so?
Why? Because, well, the ingredients for life are everywhere we look in astronomy. Water is very common. It's an extremely common planetary building block. When we look into interstellar space, the almost nothingness between stars, astronomers actually still see complex organic molecules. Everywhere we look, we see the ingredients for life. Stars can provide energy. There will be planets that have liquid water on them. And so it seems inevitable that if life arose here on Earth, that it should also be able to arise on another planet somewhere else in our galaxy. There's a harder problem, though, because I am convinced that life is out there somewhere. But the chance of us finding signs of life is a whole other question. And that's a very, very, very challenging journey.
Because if you look for life, then you look for the life we know.
It's not so much that. That is also definitely a challenge. The challenging thing is that planets are so small and faint. It's extremely hard to observe them. And we need to look at their atmospheres and assess all the gases in the atmosphere and find gases that don't belong, that are in huge abundance, and that the only way that gas could be in the atmosphere is because of life. And that's a very hard thing to do because we found thousands of planets, and that we kind of have under control how to find them. But how to find enough planets how to find enough planets that are small like Earth, and how to study their atmospheres in enough detail, that is a very hard thing to do.
So, do you have any idea how many planets are like Earth?
Right now, astronomers are constantly trying to assess. Okay, so you would not believe how many hours myself and my colleagues and other people have spent on trying to evaluate how common Earths might be. And we actually don't have an answer right now. The answer that we work on scientifically, it can range anywhere from 2%, that means like 2 in 100 stars like the sun would have an Earth, to 100%, that all stars like the sun would have a planet like Earth. We really, really don't know.
Wow, that's pretty exciting.
Well, there's a space telescope, Kepler Space Telescope, that was launched in 2009, and Kepler stared at one patch of the sky for 4 years. And Kepler's goal was to answer the question, how common are other Earths? That is, Earth-sized planets and Earth-like orbits about sun-like stars. And for various reasons, Kepler fell short of that goal. But Kepler did tell us that small planets are extremely common. Small planets that are rocky around stars like the sun are very, very common.
So did that convince you that there must be?
Absolutely. I mean, we have no doubt that there are small rocky planets out there in great abundance. But the different...
I mean, that there's life.
Oh, like... I have no doubt there's life out there somewhere. But the problem we have right now is it's only the very nearest stars, if they have planets that are close enough and bright enough for us to study. So I have no doubt there's life out there somewhere in our galaxy or our universe. It's almost inevitable just based on sheer numbers and the fact that building blocks of life are very common. But if the harder question is, can we find that anytime in the near future? Because we're limited to studying the very nearest stars to our own sun.
So,
but you can go and interview a biologist and ask them, do you think there's life out there? And they might say, no way. No evidence. We don't understand how life on Earth forms, therefore we can't even speculate.
But you must have a clue.
Well, I don't have any clues other than what I've given you. A lot of it's just pure faith, admittedly.
So, but you are very convinced for yourself that there's life out there, and the idea alone raises the imagination enormously. Life out there, there's so many films and books and
absolutely.
everything.
We just watched the movie Aliens. I hadn't seen it before, actually.
Senior interest or just
well, the kids wanted to watch a family movie, so they just gotten old enough so we can all watch movies we all like. When kids are really little, they just want to watch a cartoon. And Signori Weaver, we watched the first Alien, and then just the other night, I thought it was really scary. Actually, there's this old ship that had crashed on a planet, has these giant eggs, and everything has been dormant for a very long time. Meanwhile, there's a colony on the planet of people who didn't know about the ship until until the main character, Ripley, her spacecraft was found and she was revived from hibernation. 60 years had gone by and she told them about that. So they apparently had sent the colonists to go investigate the ship, and then all of a sudden they hear nothing from the colonists on the planet. So she has to go back and see what's going on. And these are the most scary aliens around. They're going to kill people, and they basically capture the humans to act as incubators for their new life forms. So there's a ton of them. People want life to be out there.
And what do you explain to your children when you watch that?
Well, the thing is, they weren't scared, and I was, so I don't have to explain it.
This is your field of work.
It's my field of work, right. Well, I will say we're not going to find big scary monsters, so you don't have to worry about that. How do I know? Because the tools we have as astronomers right now, we're just going to see gases produced by those aliens, gases that they breathe out, or gases that are produced by the plants that they're eating. Yeah. And in fact, we won't know what type of life is giving off those gases if it's just slime, giant fields of bacteria.
But suppose they are big monsters.
Well, if they're big monsters like those aliens, I guess suppose they are big monsters, well, if they're big monsters giving off gases, we still won't know. We'll just see the gases that don't belong. We'll do our best to disentangle that from any volcanic emission, and we'll try to understand if it's created by life, or if it's just what we call a false positive. But that's a different question now, because then that question is, can we go to the planet? Can they come here? And that is still science fiction for now. How to
because
get
you need a lot of imagination, and you need a lot.
Yeah.
How is it allowed for you to use your fantasy?
Like imagination in science, it's different from imagination in creating a film, because in that case they can imagine away the big technological challenges. They don't have to explain how Ripley and the other crew can get on a ship and hibernate for a while until they get to the new planet and land there, and everything like that. So we definitely do use our imagination, but not quite in that same way.
Because when you have this theory, or well, that if there are gases which must be produced by life, you come to a certain point at some border in this wilderness that you cannot see much more. And you have to use your imagination. So suppose I go to the left or to the right, or it's too dark to go on. But then you need some other tools like imagination or maybe your fantasy. Is it something you can use?
Oh, that's a tricky one. I'm gonna have to think about that for a minute. Like, possibly, we still need to use like our creativity and imagination in solving a problem. We have to have a vision of what we think where we're trying to get to. We have to have that. Yeah.
And when you do, what do you see?
What do I see? Well, depending on the day. No. I mean, I'm not sure actually. That question's not an easy one for me to answer because I've not thought of it that way in a very long time.
Maybe you can come up with an answer later on.
I'll have to think more about it. Well, there are definitely, I'm not totally sure what you mean in terms of like creativity or, envisioning your fantasy of what could happen. I mean, it could come at any level. Like we have the Starshade project, a giant specially shaped screen we want to put in space. And that wasn't my idea, but the people who had thought of it in the 1960s, it is kind of a fantasy because it's so far-fetched, like for that to even be possible. But, over the decades, we've whittled away at the technological progress and tried to make that a reality. But now I feel like I need to be more creative because of your question.
Well, maybe if I rephrase it, like you're on this border in the wilderness, you want to move on, but you don't know how to move on. Maybe it's not imagination, or maybe it's not fantasy. Maybe it's instinct. So
yeah, there's definitely a lot of instinct involved.
How do you use your instincts?
So there's, sometimes there's, there's two different types of instinct. One of them is, it's like when we're imagining we're in the wilderness and I see this river and I know I've got to get down the river and there's giant rapids and I think I can do this. And that's not a fact-based intuition. It's just a gut feeling. And part of it's a desperation. I need to get down that river. I'm not going to get to where I'm going. And you kind of take a leap of faith and just go for it. That's definitely one kind of tool or instinct that I've used before, actually. I have a vision of what I think will happen, but I have no idea how to get from A to B. And I have to take a leap of faith that I can do it. Even though I don't really have the tools, I'm just gonna go. The other intuition I have experienced is one of accumulated success with that first type of intuition. And then I know I can do it even though I still don't have the tools. I know that I've been able to find the tools and that I can still do that one more time again. So intuition is a huge part of finding your way through here. And
are you blessed with a big instinct? Or
I think so, yeah, actually. I think it's a little touchy because, okay, I can't speak for my colleagues at MIT, but I'm pretty sure we're all often accused of being arrogant. So I don't want to come across as too arrogant, but yes, I think I'm blessed with a special intuition in that. Because it's that everybody has it, actually, and most people ignore it or it's hidden or they don't use it. It's that gut instinct of this is right. I feel this is big. I'm going to do this. I know this is going to be big. And I've had that feeling many times. And yeah, it's not part of this interview, but I love talking about Charles because he and I had a great time. We first met. I had my gut instinct about him, from almost the second I met him. That's a sort of different thing, but many more people will understand that. But yes, I have that in science, and I have that about this project that's not as related to finding life elsewhere of all the molecules. And it's wonderful now because I'm able to trust my instinct.
Is it like instinct you need to survive? Does it have to do with survival?
More like success, actually. I think it would be more like an instinct to succeed. Because I think survival is just like, how do I get enough money to get food? I've got to make sure my children are safe. I think those things also involve instinct, but it's more, it's like the next level. Now that everything's okay and things function and I'm not worried about surviving, what can I do to just be a super achiever and make impact and reach all my dreams?
So now you're well equipped.
I'm very well equipped now. And so
what can we expect?
well, I'm having a moment of self-reflection because now I feel like I need to do more. That's the ambitious person's problem. You always feel like you need to do more and get more done and do bigger things. I was in a bit of a rest period, though, in my career, a resting phase now. So I wasn't thinking in that way. I was sort of taking some time off, not time off, but, not working 24/7 and going all out.
But when you go all the way again, can we expect from you?
Well, my main thing I'm working on, what you can expect is that in time, I'll be able to report to you one way or the other whether or not we think we have found signs of life on another planet.
That's a strong one.
Mm-hmm. But that wasn't tomorrow. That's like 20, 30 years from now.
And you're sure?
I said I can report one way or the other. So I may come back and say, around the nearest 30 stars, I might be able to say we have planets like Earth. We found 5 of them. We've studied their atmospheres. One has a suggestion that it might have a sign of life, but it's not good enough for us to say anything for sure. I might come back and report that. But at least I will have answered it one way or the other for the nearest stars that we have.
Well, that's pretty exciting.
Right, but it is ambitious. It's like us saying here as a group, we've just decided to go to the North Pole. We don't know how we're going to get there, but we think we can do it.
Yeah.
So a lot of things have to work.
But then when you compare it to colonizing the United States or discovering, and then you get here, and then you see all these Indians and you have to talk to them, communicate.
Right.
That's not another life form, but it was alien in those days.
It was alien. Mm-hmm. Right. Well, I'm not. Yes, that's right. It was alien. Yeah.
But can you compare it with that kind of exploring for people who don't have these instincts or this fantasy or imagination, that they understand what you are doing? Or it's like discovering a new world.
Right. Mm-hmm. Right. Okay. Let me think.
Is it like that you find another Earth?
Like yes and no, because we're not finding the Earth like we're going to go there. Not us. Maybe someone in the future will figure that out. But we're not going to go camping, or we're not going to go there and work through the wilderness and find giant monsters. It's just, half of it's in our imagination. We're going to see a point of light, like just a pale blue dot or a pale red dot or just some little tiny thing. And all the interpretation we get, we're, like we started out talking about, we're interpreting what we see. Yeah. We can't guarantee this all. We're not going to have pictures of civilizations or the Great Wall of China equivalent or pyramids. We're not going to be able to see any features like that. We're just going to see a point of light. We're going to know it's orbiting a star. We're going to be able to say something about the mass and size of the planet and what's in the atmosphere. What kind of air does that planet have? And we're going to put a picture together based on scientific tools. And that's how we're going to know if we found another Earth. So it's our modern day version of exploring. Yeah. We've explored pretty much every landmass. Parts of the oceans remain unexplored, but we know our planet very well right now. And space is a vast frontier that's still out there for us, waiting to be explored.
What do you think? Because you don't have to prove this, but what do you think that in future, any amount of time, we will be living outside there, or we will colonize other planets, or will we be colonized, or is it possible to think like that?
It's starting to be possible for sure. I mean, it's the first time ever in human history people have considered sending probes to other star systems. It's still quite a ways off. I believe someday humans will find a way to get there, but it may be hundreds or thousands of years from now. I think our desire to explore is just so tremendous that as humans, we want to go, we want to explore. We first have to go to Mars.
Do you want to go?
No, me, myself, no. I don't want to.
No. You don't want to go to Mars or into space?
I don't want to go to space, actually. I know that sounds... thing is, I don't like small spaces, and I don't get along all that well with other people. And I just don't want to be confined to a little tiny spot for for decades. So space isn't for me.
Your own.
A spaceship of my own, maybe. Yeah.
A one-seater. Well, let me have a look at the things I wrote down. A lot of questions are already asked. Can you, because you said when you look at my office, it's beautiful to see. But
The view,
when
yeah.
we are there, what do you actually do?
Well, let's see. What do I actually do?
Describe what we see.
When I'm working there? Well, I often work on my computer, which programming or just other things. Meet with students and my research team members. We talk about things and try to figure things out.
But I mean, when you're at your office on your own and you only have your own mind.
Oh, I'm thinking.
And
Yeah. I'm usually working, and the best thing is I'm in the zone. You know, when you're in the zone and the world goes away, you know you're doing your best work.
I'll try to explain that to me.
Okay, well, I think it happens like when you do your very best work and you're right where you're supposed to be, then everything else goes away. It's just like you and yourself and your work. And really just what happens is you might get a knock on the door or a phone call and you snap out of it. And you're like, oh, I didn't even realize, but I wasn't aware of the world around me. I was just involved with what I was thinking.
And then you are in?
And then I'm in the zone.
In the zone?
Yeah.
That sounds like a movie in itself.
Actually, one time, the first time I was in the zone, actually, that I realized it, I was in high school and I was played in the band. And I had a piccolo. It's like a flute, but it's smaller. Actually, I can't remember if I was playing the piccolo or the flute, but the flute sometimes gets a special role. It's like the singing voice because it's so high. And at the very end of this piece, I had to play. It was just me. And so I was kind of obviously nervous and stuff. And one time I even missed it entirely. But I had to get that. And I realized when I finished that little phrase with the flute, I was like, oh my gosh, there's a world here. There's an orchestra. But I actually had been lost in this sort of perfect non-thought process of just being and playing the flute.
Like a harmony.
Like a harmony. Mm-hmm. Like things were just happening and I wasn't aware of it at all. So if I can get in the zone, I know I'm getting my best work done.
So can you is that the decision you make? This afternoon
Right.
I'm entering the zone.
We're almost entering it. So, when you enter it, if we're just talking and these folks here go away and I forget about Charles and I'm not worried about the kids getting home, like his phone you didn't hear it, but I looked at his phone and it's one of the kids actually has a job. He's 11, but he has like a babysitting job down the street. So that lady just wrote to him. So I'm not in the zone if I can hear that phone and I see Alicia wrote to him. Or what time is it now? Diana, we have a babysitter she'll be coming soon. And if I'm not thinking about that stuff and all I can see is you and the question, and I'm like thinking about the question and I'm not, then we're in the zone. So we could get in the zone. Mm. In fact, the best interviews and like if you're, if they want to take my photograph, it's very hard to do because you can't be like in the zone unless you can get in the zone and like really give to the camera. You can't, the interviews or the pictures just don't come across right. It's very difficult actually. Now, how do I get in the zone? Like I need a good night's sleep. I need to not be worried about other things. I've got to put my phone away and not be distracted. I need to clear out all the things I'm worried about. If I've got to answer an email or get a phone call out of the way, or if I have a negative confrontation that has to happen at work, I've got to do all those things. So I can't force myself to be in the zone, but I can create the right environment so that I can focus.
And now it seems like you can focus very well right now.
Right. It's because you're such a great interviewer. I wasn't expecting this level of question, so. Yeah.
Thank you. I'm just curious because I have no knowledge at all. I just try to be in the position of our viewers and
right.
If I understand it, they can understand it.
I understand.
So, but it's so interesting what you tell about being in the zone. I can imagine something, but it's new.
But I feel like everybody has it, and you might not know it.
That's why I understand what you mean. That sometimes you are in a flow or in the zone.
Yeah, in a flow. Like I used to whitewater paddle, and if you're in like a hard rapid, you have no choice but to be in the zone. Because like you have to make these really quick decisions and there's big waves and you feel like you're part of the river and everything's just happening. Then you finish and you're like so happy and you made it through and that thrill and that scaredness is kind of gone. You just look around like, wow, okay. But that moment that you were in the rapids figuring out what to do and going, it was just pure being, like pure living. Yeah. I think Olympic athletes must do it as well. I think in their case, they're in the zone, you know, they're not thinking about dinner or like what they have to do when they get home.
But then you must be very well equipped also with a character or that you can allow yourself to be there. Then you must not sense any problem or coming problem or any argument from somebody else or maybe something like I'm on the wrong path. That's also possible, of course. That you.
I think I'm just good at
Can you be in the wrong zone?
A lot. Mm-hmm. Like the zone is very special and doesn't happen all the time. But I'm very good at compartmentalizing. Like if I have a problem, I can just not worry about it for a while, unless it's a very big problem. Okay, so I have thought about this, but I haven't really talked about it before to anybody. I do see being a scientist like being an Olympic athlete. Like I need big periods of rest where I literally just do nothing and I let my brain just, like it's not watching TV, it's not reading a scary book, it's just like nothingness because I've got to rest my brain. And I feel like I do know how to, you know, take care of myself so I can get where I need to be to do great work. But it's like recharging your batteries, you know, doing nothing, not really thinking, just some quiet time. I don't mean meditating or anything. I'm just thinking like I'm at home, really hours are going, like what I did this morning. Just didn't really do anything.
But to me it seems much harder thinking about nothing.
I'm not necessarily thinking about nothing, like I'm cleaning up, more minor things that don't require a lot of brain power. You know, cleaning up, doing some laundry, you know, making plans for whatever I have to do later.
So you're also parking your research.
Yeah, parking research, exactly. Like I liken it to an athlete who you can't be training all the time. I mean, that would be negative. That would be negative for doing well, actually. You need to rest a little.
So when are your Olympics?
When are my Olympics? Okay, no. I don't have anything equivalent to the Olympics because we're not competing, you know, on the 1 kilometer race or 400 meter dash. But when I want to be in the zone and do my best work, I have to be, you know, ready for it. So I'd say that would be my equivalent of the race, is the time when I'm really trying to work.
But is there something you can compare with a gold medal, like proving that there's life out there?
Well, it's probably not the best analogy, actually. But it does take a tremendous amount of energy to think. It sounds funny saying that, but like if I go to work and I think really hard all day, I actually come home completely exhausted. Even if I've done no exercise, haven't walked upstairs or haven't, you know, hiked all day. It's that same, like people know if you go on an all-day hike or you do some major thing physically, you can just be wiped out at the end of the day and like ready to fall asleep in an instant. But thinking actually, when I think very hard, problem solve, it takes that a huge amount of energy.
Does thinking never get you into problems?
In what way? Like give me a huge headache or just I can't solve a problem or?
That you think I'm starting to get crazy or something?
Oh no, I don't have that when I'm thinking about work, but sometimes I have it in other situations actually. I've seen my friends have it too. I was just at a conference and 4 of us who were friends were all at the same conference when we started talking. And one of them had that moment where she thought she was going crazy, but 2 of us were talking rapidly and we kept switching topics because we had been in an email chain about a project we're doing. And she had thought she was just losing it. But when we explained that we had 2 different conversations going on and we were jumping back and forth, she felt relief. So sometimes overthinking gets you in trouble that way because you think you might have gotten very confused about something, but you find out that it's not you, it was the situation.
Wat is piekeren in het Nederlands? Doubt. No, and whenever you doubt, trying to figure it out and you don't succeed in figuring it out, don't you ever get mad of yourself? Oh, there must be a solution and I cannot find it. Or
Okay, let me think about that one.
think.
So there are a lot of cases like that. There are a lot of cases like that where you go down a path. Imagine it's like exploring in the wilderness and you just can't get through. And you have to back off. And you park it in a way I'm thinking, I want to go there again in the future. And I do have one particular problem I can't figure out, actually. Unfortunately, we couldn't, even when I asked my best student from the past, great with physics, the two of us even couldn't solve this problem. And the reason is because we're trying to describe a situation in which the limits a planet can be stable. A planet could be unstable and just evaporate. If it doesn't have enough gravity, it can't hold on to its material. But the equations we're using only describe a planet that is bound together. So we don't even have the tools in this. This is a good example. We have no tools and we don't know how to handle this problem. So I decided to leave that problem. I didn't get mad. I kind of got a little mad. I would only get really mad if someone else figures it out and publishes it. But for now, instead of me, because I know it's a great idea, but I'm not 100% it's a great idea. So I'm waiting for more data to accumulate so I can know whether or not this idea is good.
You just mentioned the idea of parking a problem, but how much does it happen that you have to park an idea?
Often, very often.
Why do you have to park an idea?
Often there's, okay, let me think for a second. Sometimes it's a practical reason. I don't have time or resources or people, to carry out that particular problem. Other times it's just not a priority. One can have so many ideas and just not nearly enough time to pursue them. And other times it's just too hard. The kind of tools that we'd have to develop to work on it, or just figuring out the right physics we need to solve the problem is beyond what I can do. Sometimes it gets parked forever. Sometimes it's parked till I meet the person with the right skills, like my biochemistry colleagues, who I can work with. Other times it's just parked until the summer, until I have time that I'm not teaching or dealing with university tasks, to just have some time to think through it.
But I can also imagine that you feel sorry for having to park a problem. That you have an idea and that you think, parking an idea, that you have an idea and think, wow, this is promising. There must be an answer there. If I just had some time or a team to help me explore this.
Right. Sometimes it's definitely frustrating. But part of life is choosing what's important and what's not. And so, sometimes you just have to choose the one that's important and go with it. It's also harder now than it used to be. I think when you're younger with less responsibility, you can just drop everything and focus on that problem you think is so important and really make traction and finish it. And now there's just so much going on in just my job and home that it's harder to just drop things, to just focus on one thing.
When you are in the zone, you are there at your desk, no one else, you're alone with your own mind, and you are equipped, thinking. Can you try to explain me what happens then in your mind? Do you see something, or do you try to see equations, or do you see colors, or do you feel something? What is the reality in the zone?
Well, I've never tried to articulate it before. Okay, sometimes there's a flash of, not colors or light or anything, but there's a flash of thinking, like a conclusion gets reached in advance of getting there.
A conclusion gets reached?
Yes, it's kind of like I'll be working away at something and then I'll kind of get that almost, like the only way I can describe it in the best case is like I realize what the answer is before I get there.
Then you have to find out how you get there.
I have to find out how to get there. Sometimes it's a negative. We're in the zone, I'm working, and I just realize it's not going to work. But I still want to do my due diligence and make sure that this idea is not going to pan out.
The have to be sure that it's not right.
Have to be sure that it's not right, or right even in that case.
But when you close your eyes, when you're in the zone, what do you see?
I don't know if I can answer that, actually. I don't know.
So, somehow, I think scientists and artists have the same way of thinking.
I think so. Well, what's the way the artists think in the zone?
He's somehow looking for truth and expresses that into any kind of art, and he's very he has to make that painting or the sculpture or whatever,
Right.
because that's what for him means the truth or reality or anything. And but the only difference is that artists follow other rules, but they're also looking for truth. Like you are, I think you are looking for truth.
I think so.
So, because you're always searching for truth, you will probably never get to know how it looks.
I see.
Isn't that frustrating?
No.
Really? Because the truth is always bigger or further away or...
The thing is, I feel like I'm one person out of a long chain of people in all directions. And so I feel I'll be satisfied if I can accomplish, my goal or my life's work, as long as the next person in front of me is ready to go. So I may never reach what truth is or what I set out in the biggest sense of the word. But as long as I know it will be carried on or someone else will keep the search going, I'm okay with it.
Okay.
Yeah.
Now maybe go back to a little more concrete things or practical things. So you were researching data which come from... Where do these data come from?
The data that my team works with come from the Hubble Space Telescope and the Spitzer Space Telescope.
And how do these data look like?
Well, the ultimate form we want to convert the data into look like points on a graph as a function of wavelength. So we have visible wavelengths where I can see and infrared wavelengths where heat cameras can see. And each point has an error bar associated with it, an uncertainty of the measurement. And so we just kind of have data that as a function of wavelength, and we look for patterns in the data. Another set of data we use is a time series of data. And these data come from the Kepler Space Telescope. And they're a data point taken every few seconds, but it's been to 30 minutes. And it's on a time sequence. So we have one point of a star, how bright it is, as a function of time.
In seconds instead of 30 minutes?
These are mostly in minutes.
Oh, okay.
Minutes. But each point will be every minute or every 30 minutes, depending on which mode that particular target star was observed in.
And I would like to go to this point where you can tell me about this, I don't know if it has a name, but I call it the sunshade.
Right, we call it the star shade.
Star shade.
Call it the star shade,
yeah.
right.
But I compared it to this thing. It's a sunshade. We call it the sunshade
Okay.
for the camera.
The baffle.
This black thing on front.
Yeah, we call that a baffle.
Ah, okay. Because in 2017 or 2018 there will be a test satellite.
Tests, right.
And so what can you tell me about that?
Okay, well, first of all, just to back up a little, there's many different telescopes and projects that are ongoing. Different groups of people all around the world have different projects they're trying to move forward. The ones I'm involved with, one of them is called TESS, Transiting Exoplanet Survey Satellite. And TESS is a NASA mission. It costs $200 million overall. But for space, you have to imagine everything costs 100 times more than on the ground. TESS is TESS is a satellite that will orbit Earth. It has a very elliptical orbit, so it can spend most of its time away from the heat and light from Earth. It'll zoom around while it downlinks data, and it'll spend 13.6 days away from Earth and a few hours zooming by. It'll spend each of 2 orbits on one patch of the sky. And in 2 years, TESS will survey the whole sky, looking at stars, measuring their brightness as a function of time, searching for planets that transit their host stars. They go in front of the star, and they block out a tiny amount of starlight while they're transiting. And the goal for TESS, actually, is to uncover a pool of planets, of rocky planets, transiting small stars much smaller than the sun. And those stars and their planets are the first ones that we'll be able to search for signs of life in the atmosphere using the James Webb Space Telescope, which is the next Hubble Space Telescope, if you will. So we're working on our very practical plans to find the planets around stars that are close enough to Earth so they're bright enough, and we'll look for signs of life in their atmosphere using the James Webb Space Telescope.
So again, this satellite is able, maybe you can explain it again, how it blocks the light.
Okay, so the star shade is something totally different. So we'll talk, that's way next generation after TESS.
Oh.
TESS itself is actually, you know what TESS is? It is just 4 essentially specialized telephoto lenses. They don't focus, they're just fixed. They have about 7 different lenses inside. They're made almost to be perfectly for no vignetting. They're athermal, so they're not going to heat up or cool down in weird ways. And there's 4 of them attached to a single platform. And those telescopes, believe it or not, those cameras, they cover a strip of sky 90 degrees by 24 degrees. So it's like if you look at the night sky, it's like from your horizon all the way to the pole, almost that whole strip. And it's going to do 12 of those all across the sky. And what TESS is looking for is it's just measuring star brightness as a function of time. Every few minutes or so, it'll have a data point. And what TESS is looking for is a special configuration of planetary orbit. We call it a transit. It's when, if we have a star, the planet goes in front of the star, as seen from the telescope. And while the star is just a point of light, it will drop in brightness by a tiny, tiny amount, 1% or a fraction of a percent, when the planet goes in front of the star. And that's what we're looking for. This has been pioneered already by the Kepler Space Telescope, which found thousands of planets that transit the star. And TESS is repeating that experiment, but with stars that are much closer to Earth than the Kepler stars are.
And where does this star shade come in?
Well, you know how the star shade comes in is, right now, I want you to know about these transiting planets are very important. They're really the main thing we're doing in exoplanets because they're easy to find. But they have to be specially lined up. Planets' orbits and the stellar spin axes, it's all random. Stars are born they can collapse this way or they can collapse this way. So transiting planets are very special, and they're also quite rare. Our own Earth, for example, is so far from our star that if we're looking for an Earth-Sun twin, only 1 in 200 would transit. An analogy for you is like throwing darts at a dartboard. If you're really close to that dartboard, you can easily get to the center of the dartboard. But the further away you go, the harder it is because your angle's smaller. So for Earth and Sun, it's actually quite rare that they'll transit. And so if we want to find an Earth twin, if we want to go beyond transiting planets, we actually eventually have to use a totally different technique than Kepler and TESS and things that are going on now. We have to be able to block out the starlight so we can see the planet directly. So in exoplanets, it's complicated. We have many different ways to find planets, at least 6 different ways, maybe 7, maybe 30 if you read Wikipedia. But it's so many different ways, and they're all for a different goal. Transits are something we can do right now, today, that they rely on a very special configuration. And just to be a little more technical, for a transiting planet, the drop in brightness is related to the area of the planet compared to the area of the star. Because that's how much light we're blocking out. Imagine like a big circle, that's the star, and a little circle, little disk, that's the planet. Our own Earth actually blocks out about 1 part in 10,000 the light of our sun. If there's an alien civilization looking back at us and they have a Kepler Space Telescope, They need to measure a star to a precision so they can see a drop in brightness of 1 part in 10,000. It's pretty small. Well, we are detectable because our Kepler Space Telescope can detect.
But they don't have a Kepler telescope.
Who the aliens?
Yeah.
Oh, they might. They might actually. Because Kepler was the easiest telescope for us to build, actually. So I'm just setting the stage for you to see just how hard planet finding is. 1 part in 10,000. I mean, do you ever have to measure anything to 1 part in 10,000? Like when you're building a renovation or you have an art project, you're not measuring things to 4 decimal places. It's just not happening. Now, if we want to forget about transiting planets for a moment, because they're rare, and we may run out of them if we're looking for an Earth around a nearby sun, now we have an even harder problem. Because our Earth in reflected light, in visible wavelengths that where our eyes can see and where stars are bright, Earth is 10 billion times fainter than the sun. So it's no longer 1 part in 10,000 we're worried about, it's 1 part in 10 billion. And the reason is it's not just the area, but light drops off. If you're shining a flashlight outside, the beam is spreading out. The light is dropping off, actually. It's weakening with distance. And so the sunlight has to travel that distance to hit the Earth, and that sunlight is weakening. And so that reflected light from the sun, from an Earth-sized planet, is very, very small. So imagine we're looking for a planet like Earth, and it's faint in and of itself. But that faintness is not our problem in astronomy. It's the fact that the Earth out there we're looking for is right next to a very bright star. The star is 10 billion times brighter. So we have to suppress the starlight or block out the starlight to 1 part in 10 billion. So the star shade, if you will, is like our next step after we finish with translating planets. We're going to do what we call direct imaging. We're going to block out the starlight so we can see the planets directly. And we already do this from ground-based telescopes. Only we're reaching 1 part in 100,000, not 1 part in 10 billion. So we have many more decimal places. Still difficult. Yeah. So the star shade is going to go to space, and it's going to have to formation fly tens of thousands of kilometers away from the telescope, and the star shade is a very specially shaped screen that's tens of meters across. And this whole thing will line up and block out the starlight so that only the planet light is entering the telescope. And the star shade will move across the sky and realign with a new target star over and over again.
That must be exciting, if that works.
It's going to be exciting. It's going to work.
It's going to work. Was it your idea?
The star shade was not my idea.
But you work on it.
Yes. Recently, I led the team that was running the Starshade project for about 2 years. And we actually brought Starshade from being a crazy concept, like someone's vision or dream or fantasy, into mainstream astronomy. And we were able to pull together all the groups who have been working on Starshade, making technology work here, testing Starshade in the desert there. And we kind of brought everything up to a level now where it's surprising, just in a couple of years, astronomers no longer say, Starshade? That's dead. It's never going to work. They're like, of course we want to try to do Starshade. And this actually project I led was a study, but a NASA-sponsored study. We can get into more details if you want, but that's how I was involved with Starshade.
Maybe we can do that at the
Yeah, because you know what? Yeah. What's really cool is I have one of the petals of the Starshade prototype. It's 5.5 meters.
That big?
Well, because the whole Starshade, depending on what version we will get funded in the future, could be 30 meters across. And each petal is these particular ones are 5.5 meters. I can show you some videos later too that will help explain it. Yeah, so I have the Starshade petal, and I have another artifact. I'm not sure if it'll get back on time because I was in Washington on the weekend, and the one, but I have a 1% scale version. It's about 1 meter in diameter.
From the whole Starshade.
It's a Starshade 1% size.
And it moves?
It doesn't move. This particular one was used in the desert. It's just like a piece of metal cut out.
It's a real one, and
it was used in desert testing, where Northrop Grumman Corporation sent a team repeatedly out to the desert in Nevada. And they're trying to make sure that the math works, that the Starshade in the very special shape really does block light the way we expect. And they'd have a camera, an LED fake star and planet, and the Starshade blocking out the light of the star so they can see the planets directly. I can send you some photographs on this as well, so you have the whole story together.
We can have a look at it tomorrow. We'll finish with some questions because I think we're talking about 1.5 hours now. But When you dream, what do you dream about?
Okay. Like literally when I dream, or you mean figuratively when I dream about the future?
Literally.
Oh, literally. The funny thing was yesterday I dreamed I was at a conference and just wanted to go home. So that's kind of my usual life story. I'm on a trip somewhere and I just really don't want to be there. One of the so my dreams are really not
But
that.
That's very realistic.
I know I do. I tend to dream
It's
about.
not a dream.
I know.
It's a wish.
That's right. I have a very realistic dreams just about my everyday life. Like when I'm sleeping, I'm not dreaming about some great adventure of meeting aliens and stuff. Like in this movie Aliens, Ripley, the main character, constantly is dreaming that she was harboring one of these aliens. Because they use human bodies as hosts and it's breaking out. So I don't really dream, literally dreaming like when I'm sleeping that I'm finding a planet or anything. Unfortunately, no, my dreams are quite tedious. I don't usually dream about that.
And when you dream about any future development or discovery, or what do you dream in your wildest dreams?
Okay, well, I'm a more pragmatic person actually, so I actually need some time to think about your questions. They're so good, but let me think. I do have a dream though.
Take your time.
Okay, I'll take my time. Well, in my dreams, planets are everywhere. They really are. And they're just waiting for us to find them. And I literally dream of the data we're going to be getting. And I know it's not going to be spectacular data. It's going to be, our first try. And I literally dream of the data coming down and finding what we're looking for. And I believe in my dream so strongly, that we'll be finding oxygen and other gases that don't belong. But my dream goes a lot further because at some level, I do know I may not accomplish everything I want in my lifetime. And so my dream extends to my students, some of them who are really like my own children. And I want them to carry the dream on, actually. And so I do dream of an amazing future, well beyond what I'm going to accomplish in my life, where we have incredible things happening in space. We have self-assembly of space telescopes. We can make telescopes that are bigger than anything we imagined. Fabrication in space, where we're building giant telescopes. And I imagine the future of having just such great data that the generation just beyond me can have unequivocal, wonderful, beautiful data, that the signals are so strong and there's no question that they're seeing spectral features and that they can sort through all the different possibilities and make a robust claim of life on another world. And in my dream, I'm still alive then. I'm just 100 years old. With my husband, Charles, traveling around to conferences and getting to enjoy the success of the seeds that I planted. And I wish my student Mary was around. She actually was in the Netherlands, actually, at LOFAR, this big radio telescope you have there. It's spread out all across the country. Now she's in Belgium, but she's one of my people, actually, my proteges. She'll probably... No, unfortunately, she's in Europe right now, but I'm just saying that she would... there are some of my students I'm really attached to, actually, who I'm training for. Obviously, they're not going to do just what I want them to do in their life, just like real children, they don't go and do what you have a plan for them, and they usually don't do that plan. But I do see a great future.
You didn't do what your father wanted.
Exactly, like I didn't do what my father wanted me to, yeah.
So, do you secretly wish your children follow your...
The thing is, academic life is quite tough, actually. You're going to see me so successful, and it looks like a great life, and I have time, and I can do whatever I want, and I have a lot of respect. I can do whatever I want, really, and people won't cross me. But it's hard to get there, and so I'm not sure if I wish that life on my children of just kind of struggling and low pay for a while, and really, I want them to find something that they love doing, that they're good at, because I think that's what needs to be successful. I think as a parent, too, it's a little more practical. And I hadn't realized this about why my dad had the reaction he did when I told him I wanted to be an astronomer. As a parent, you want your children to be self-sufficient. You want them to get out there so you don't have to support them later in their life. You don't want them moving back home. You want them to be out there and launched, we call it, and just doing their own thing. So I have a vision for my children where I want them to find a job that works for them and a lifestyle that they want. And I recognize it might not be the same thing that I want for myself. But of course, all that said, I do secretly hope that one of them does carry on my dream. Like I'm gonna have to look into that. I love the story of the parent and child like growing up and working together, but I feel like they need to carve their own path.
Yeah, that sounds beautiful. Why are planets round objects?
Planets are round because they have so much mass, their gravity wants to pull them into a sphere.
Clear. Are there all these exoplanets? Do they have names?
Okay. Exoplanets scientifically get named after their parent star. So, for example, we have a star called Upsilon Andromeda, and when planets were found, they're named Upsilon Andromeda B, C, D. Not too exciting. And to confuse the matter, planets aren't named in order of their distance from the star, but they're named in order of discovery. So you might have planet B out here, and then C, and then D. That makes it very confusing. We have other stars where the stars themselves never had names until a planet was discovered, such as Kepler 186. That would have been Kepler's 186th star with a planet found around it. And those planets would be called Kepler 186 B, C, D, E, F.
And can you explain to me what is the Goldilocks zone?
Mm-hmm. But I'm going to finish the naming question. Okay.
Yeah.
Because for a long time, we wanted to just name the planets ourselves. But astronomers, we don't have the right to do that. Even if I discover a planet, I can't name it after my child or pet or anything. It's actually not allowed. And at one point, astronomers started to name them, and other astronomers got angry. Well, you didn't discover that. I work on that planet just as much as you do. Why do you get the right to name it? So people got all upset about it. But recently, I'm pleased to tell you that the International Astronomical Union, the international body that's responsible for naming astronomical objects, opened up a competition to the public. And they let different groups first register. So individuals weren't allowed, but you could be like an astronomy club or a school group and suggest names. And then people were allowed to vote on which names they liked. And so eventually a bunch of the planets were named. The stars and planets were given names.
Were you also thinking about names?
Like I wasn't actually. No. In fact, we were not thinking of them. To be honest, to remember the name of 5,000 different planets is way too hard. And so in the scientific sense, we actually like our original naming system. Because if the star is named HD 189733b, if that's the planet name, we know that it's a sun-like star, because HD is after a catalog by a man named Henry Draper, who went out and cataloged all the bright sun-like stars. If it's Gliese 581c, Gliese was another person who named all the red dwarf stars. Then we know it's a red dwarf star. If it's Kepler 186f, we know it's from the Kepler survey. So the names, as arcane as they may sound, they actually work for us.
Yeah, it's more like a code.
More like a code. Yeah. The code is more useful than an actual name.
Suppose you explore space, the universe. Is it possible that you find something or have to conclude something that you were completely wrong?
It's certainly possible. This has not happened to me yet, but it has definitely happened. I'd like to give you an example of where it happened in exoplanets. One thing that we don't understand how planets form, because we all expected going out there searching for planets that we would simply find solar system copies. A star, Mercury, Venus, Earth, Mars, bigger planets, Jupiter, Saturn, Uranus, Neptune. And wow, astronomers found Jupiter's where an Earth should be, or Jupiter orbiting its star 10 times closer to its sun. We found Jupiter's 10 times closer to their star than Mercury is to our sun. We found what we call hot super-Earths, planets so close to the star, the surface should be hot enough to melt rock. And we see planets with 1 day period orbits. Their year is only a day. So we found so many planets, it's just crazy. Now, when people worked on planet formation, first of all, they never predicted this huge range of planetary systems. And the funny thing is that these planet formation theorists would say, we predict there will be no planets between 1 to 4 Earth masses orbiting at some distance to their star. And they constantly made predictions like that as soon as our telescopes, our instruments could reach smaller planets, their predictions were just completely wrong. So it actually has happened over and over again, at least in that field, where people predict things and they end up being completely wrong. So I gave you an example. It's obviously easier to blame other people than it is to think of your own work. But it is possible. Okay. It's certainly possible that you think of something and you have a plan. You imagine something and you work it out and you're sure you're going to find it and you don't find it. It can happen.